basically you went to the drawing board, you overlaid with like tracing paper and said, this is, let's say it's say part of a wing. And then you got the paper output and you go back to the drawing board with your tracing with colored crayons to try and get some idea of the stress distribution, the deflections and so on, compared to the so-called glory days of the 70s or 80s where people would charge what they like for, software almost, because you're sitting on a, $15 to $20 million mainframe to do this analysis. So I got to pay $500,000 for the software. Seems like a good fit. We used to lose people from the stress office. We would try and get people to come into the analysis team. After one analysis, they'd run through. I'd say, "Do you want to ready to do the next one?" No. And they'd run off to do the, the detailed stressing job or whatever it was. You want to unlock the power of the solver, but then as the solvers have got more sophisticated, the things we're doing now are more sophisticated. You need a workflow to wrap around that. And the trouble is, how do you define that workflow in a general sense? A preload, I want to do a thermal analysis, then I want to step into a nonlinear analysis, and then this chain of analysis types, spawning different analysis has become very much more of a complex environment, and people expect to do complex nonlinear analysis out of the box using this let's say this pre-solver and post environment. Is the simulation in step with this? And I think the fundamental piece of advice is that every simulation is guilty until proved innocent. I don't trust anything coming out of this analysis until I can get that kind of warm and fuzzy feeling about it. My goodness me, that's so accurate. That really makes sense. Look at that fragment bouncing off there. That looks so realistic. And I remember thinking, it's completely arbitrary, the way that the elements split. I could say it's a fragment of the machine's imagination, but he was sold on that. As soon as he saw that bit come spinning off and so on, I thought he was on side from then on, like a jury. That juror's on our side, I just thought.
Tony Abbey, a fellow of the Royal Aeronautical Society, has had a long and successful career in engineering simulation, spanning nearly half a century. As one of the most widely recognised and respected engineers working in FEA today, Tony has witnessed its growth from early aerospace research, where early solver hardware was priced in the millions of dollars, through to its ubiquity in contemporary product development. Originally from the UK, with early roles in aerostructures, Tony latterly moved to California, where he spent many years in technical management at FEA software vendors. He now spends his time supporting numerous companies and organisations in diverse roles which include author, teacher, mentor and consultant, all focused on FEA and its usage. Tony's expertise is far-reaching, from workflow design and simulation strategy to complex multiphysics analysis of large assemblies. Irrespective of the analysis type, he still stresses the importance of verification, as, in his own words, every simulation is guilty until proven innocent. In this conversation, we discussed the development of FEA from the early days, with tracing paper, punch cards, and even crayons used in analysis, the use of the latest tools and emerging technologies at the forefront of modern simulation, along with Tony's advice for younger engineers making their way into simulation.
Okay. We're done. You mean I can go home now?
You can go home. We're finished. If it was only that easy.
That's all you wanted. Okay.
Thank you for joining, Tony. I just wondered if you can give a bit of background in terms of your work with FEA. You've been involved with the industry for a long time, or the FEA within the industry for a long time. I just wondered if you can talk through some of the things that you've been doing and kinds of work that you've been involved with.
Wow, how long have you got? It's been a long time. The numbers just keep rolling forward. It all started for me. I went to what was then Hatfield Polytechnic, and I did 4 years on an aeronautical engineering degree course. And there, one of the tutors was really involved with an old British solver code called PAFEC, and that was out of Nottingham University originally. And that was my first introduction. I think that was about the second year, maybe the third year of the 4-year degree course. That was the first time I'd really heard of finite element analysis. at that time, we were just coming out of the old force method with a gyrus. Had been a lot of work there. So one of my tutors was pushing the old force method, where you basically assemble flexibility matrices and solve for them. But that was really a non-starter. So it kind of, by the time I kind of graduated, then I think PAFEC had really started to come on, and that was my first intro to it. But it was very manual, very labor intensive. It was even before card decks. It was actually, it was very kind of clunky. Then I did a master's at Imperial College, and by that time, we'd started to be able to code our own little FEA solutions and things like that. So that started to grow. And FEA was really, so this is like 76, I graduated with a master's. And then I was very fortunate. I got my first job was at British Aircraft Corporation up at Wharton in Lancashire. And there were two, well, really a bunch of key people there. They just started an analysis group, had been kind of bubbling up over the previous probably 5 or 6, 7 years. So there was a whole bunch of people there that were almost like pioneers within the UK. And at that time, a lot of the aircraft companies, even the divisions of British Aircraft Corporation, had their own FEA solver. So you had these homegrown solvers. So when I joined BAC, we had those called Wharton General Displacement Method, and I was part of that team doing real work on aircraft, major chunks of components. But Nastran was just coming along. Because we were multinational working on the MRCA, that what became the Tornado, we had the Germans, the Italians, the Spanish, and us. Nobody could agree to use a British solver or a German solver, or whatever it would be. So they decided to go for Nastran as the neutral. And MSC had just really started to commercialize that, I think, a few years before. All the people within Wharton were saying, who were in our method, were saying, well, it's very inferior to what we're doing, which it was in many aspects. But if I wanted to make a change in a deck or what do I do here, there, or wherever, I had to go to the big lever arch paper file and say, okay, that's what that card does. This is what this does here. I could go and talk to the expert, but there was no real documentation, whatever. The MSC stuff, perhaps slightly inferior, but beautifully documented, and you knew exactly what you're doing. So that kind of stream went this way, we went this way, and then I was there for about 3, maybe 4 years. I did a lot of interesting stuff and gradually migrated into what became the kind of like the Nastran community. So lots of interesting stuff. So that was really a big kickstart for me. It was days of simple models, 300 elements was a big model. It would take a week to turn around. Doing fracture mechanics, doing du by dA meant 2 models, trying to find the difference between those numbers. It was a special process within the computer room. So like a week to turn that around. But, that was really, the starting point for me.
In terms of the user interface to what did you call it, the Wharton displacement method?
Yes. Yeah.
And the Nastran method. So how did you what steps were involved in defining what a model was going to look like then? Was this all input deck text editor related then?
So there was no text editing at that point. It was all input deck. So basically you went to the drawing board, the designer's board, you overlaid with tracing paper and said, this is, let's say it's say part of a wing. You actually sketch that out and you're actually drawing the nodes and the lines and so on to represent the elements. So then you went back and you had a coding sheet. We actually put in the coordinate system, put in your connectivity and all of the different, job control forms, material properties and so on as an overlay. They were very different between Nastran and the Wharton method. And then you had these scripts basically. And then that went to the punch card operators, a bunch of about 50 or 60 girls. As a young, and I've got to be careful what I say here, but all I say as a young man in the office, to have that pool was, it was very pleasant. Let's put it that way. So those would be turned into punch cards. You'd if it was on an expensive project like MRCA, they would be checked automatically. if you're on a cheap and cheerful project like rectification for, say, Strike Master, then you had to check them yourselves, or they were just blank cards because that was too expensive to actually put the print on there as well. So you fed that through, and then you got the paper output, and you go back to the drawing board with your tracing with colored crayons to try and get some idea of the stress distribution, the deflections, and so on. But most of it was going to be force, grid point force output to pump through to the detail stressman. Very similar kind of flow to what's in Apex right now that you're so familiar with, which is to basically saying we're going to use grid point forces as the starting point for say detail stressing work. So that was looking at a contour plot of stresses, which is something we didn't do. Deflected shapes were useful, some sense of the stress flow, but mainly providing the load path for the detail stressman to actually work with kind of downstream. And sometimes that would be me doing the detail stressing. Sometimes it was
so from a visualization perspective, then you've traced out your model, converted that into punch card coordinates and whatever necessary information is required. That's then gone somewhere else, been solved, and then you get presumably some kind of text output back. How could you visualize the deformation of a piece of structure in that way?
You sketch it out with a pencil.
So a ruler and pencil, and say this grid has moved 50 millimeters this way, and you'd redraw the thing. Okay. And then that would give you some sense of whether this is sensible or not. Okay.
I can't quite remember when flatbed plotters came in, which would then allow you to plot the results. I think in terms of, I remember in the late 80s, early 90s at Hatfield, working for what was MBA Systems at on the 146, the 125, and the early Airbuses. We had flatbed plotters by that time, and that was the only form of interaction we had to see what we'd put in and what was coming out. And a very quick story, I remember taking a view down a beam, like it was like a main spar. And unfortunately, my orientation was looking down the spar, and I plotted bending moment of shear force torque diagrams and so on. But because it was looking down this view, it became like a paper doily. I got the view wrong, basically. So I always remember the guy coming from now you call it it was the computer center. We're holding up this piece of paper where I'd actually punched like a paper doily around because I'd done so many imprints. And I said, oh dear, that was bad enough. But in fact, the flatbed plotter itself, the base, I'd actually imprint because it was just bang, 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 bang. That was like 1990. In terms of visualization, the first time I saw 3D animation and saw, I think the point you're getting at, actually saw what I'd put in was probably, that was when I worked with Lloyd's Register offshore in 1980. And after we'd set up our, offshore jacket model, which was all three-dimensional lattice work, we were ushered into this darkened room where there was this monitor, you'd call it these days, and the operator very slowly and carefully spun this model around in 3D. And we'd all be watching to say, oh, that's not quite right. Can you just spin it around a little bit more? And then we'd kind of make little notes and so on. So it's almost like an interview. You had this like a visit to the dentist chair, to actually see what your model was doing. So I can't remember exactly the chronology, but that was the idea. Probably mid-80s was when we actually started to see 3D plots regularly, and it was again flatbed plotters, paper plots of what was going on, both in terms of the deflections and also the model. And I can remember it would be around about 85, 86, a British aircraft Stevenage, BA Stevenage on the weapons system side. I had the job of specifying the next level of monitor. And these are what we call now a dumb monitor. All it did was, the mainframe was doing the crunching. It just was basically feeding back the graphics. And I was told it was a Lexi data, I think. You can either have color or you can have animation, but you can't have both. An animation meaning you could render and spin around. And the rendering took so long that there was just, you say, I want this view, and you look at it. And it was mainly wireframe. We used to have this, this parallax flip. You think you're looking at the model this way, and then you suddenly realize, because it's all wireframe, in fact, no, I'm looking at it that way. So that was one of the, you'd often see engineers at the desk sort of going, which way around is this thing?
So late 70s then, when you're doing some of the BAC work, and you're developing a 300 element model, tracing paper to punch card to computing center to back again. What sort of time duration would you be looking at to get the model or to get the results back for something like that?
Every run was at least overnight. So let's imagine like a chunk of wing, maybe 4 or 5 days to prepare the model, what we now call pre-processing. That would include writing the script for the girls to I say the girls because it was girls, to punch up, queuing that up in the job center, and you'd have racks and racks, like a marshalling yard, all these cards going in, and then a phone call from the computer center if it was an urgent job, like again on MRCA. If it was again just a concession on Canberra, then they might let you know a few weeks later. A few days later. And so that was probably a week's turnaround for a standard component, maybe like you say, like maybe 300 or 400 element job, whatever that component might be.
Yeah. So nowadays, well, you're talking, if it was a repeat job, you could probably do it in seconds, couldn't you, for something like that?
Well, when I'm doing my training classes now, I talk about the scope of the job, the size of the model, and so on, compared to the resource you've got. And I'm a big emphasis on benchmarking your own, if you're working on your own laptop or whether it's a cluster, whatever. And I say, what is your threshold of pain, which probably relates to that. So if you're a designer and your job is not to do the detailed stressing or to do the stress assessment, you just want to know I'm in the right ballpark, your threshold of pain might be 2 minutes, something like that. If your job is to do the analysis, then you might be prepared to wait, say 15-20 minutes, maybe have a cup of coffee or do something else, but you're looking for that 15 to 20 minutes. So that's the compression, I think, from a week down to, we're talking about instant gratification, basically, in that case.
So the speed, the analysis speed, is governed more by the kettle you have than the machine that you're using.
I think so. Yeah.
Or the coffee, the fancy Nespresso coffee machine that you have over the particular the computing hardware.
Okay. Well, you know what it's like, I think most people kind of watching, listening would be saying, if I got to wait more than 15 to 20 minutes for a standard analysis, that's that's getting a little annoying. If it's a big nonlinear analysis, and I understand the scope of that, and I maybe wait overnight. I was talking to somebody yesterday that was saying, I've got to wait 8 days for this analysis because I'm trying to emulate what's being done on a cluster, debugging and checking and so on. So the cluster is fast, but it's got to wait 8 days, which is just, it's a shock to realize that these days. And I hadn't realized that until yesterday, that there's this now stratification. So there are some analysis which are still taking that long because of your resource. Others are instant, so that it brings all sorts of perspectives now to making sure that you scope out that job properly. You know the power of your machine, the bandwidth of the machine. When you're setting up that analysis, you're preparing it so you're not in for a shock. I was working with a consultant a year ago. He just dived into the analysis, and it was taking 3 or 4 days to turn that model around. And the model it can never be debugged because he couldn't get into the guts of the analysis to figure out, as everything was in there, nonlinear, thermal. And you just couldn't debug it. So it's interesting that you'd think, well, if I went back from like a callow youth back in, say, 76, 77 with hair and slim, this is me saying, well, you have this much computing power, well, we can do anything. Well, you can't. You're still constrained to, a sensible limit dependent on the, the hardware and the software you're using. So it's interesting kind of comparison.
I mean, that's key, isn't it? You talk about some of the jobs that take longer to run. you need the ability to look inside and say, yeah, that started off correctly, and I am confident that I can leave it for 8 days or whatever. What you don't want is a black box that you leave for 8 days and then it comes out red instead of blue, and that's a problem then, isn't it?
It is. It kind of reminds me when I worked at Rolls-Royce and Associates, Rolls-Royce at Rainsway, which look after the nuclear propulsion plant within the Royal Navy submarines. And there it was, again, that was like mid-90s. So using like Dyna 3D for impact work. So if you've got like a flask coming down, that would take then an overnight run. So you try and get the job set up by, say, early afternoon, get it in there, and then it would be an overnight run. You come back in the morning, and one of the worst things you have is this flask comes down. You haven't set the contacts up properly, so it just keeps on going. So you've just wasted all that computing power, proving at force equals mass times acceleration.
Yeah.
Used to be quite funny. People used to come in the morning and you'd have, by that time, it's obviously graphical terminals. You could see what's going on. So everybody would be kind of getting really big in front of their monitor here to kind of hide that first run, because if it did pass through or something crazy happened, everybody, all these other eyes are watching, and then you'd kind of get pilloried. Like, oh, what did you do there? And it was like, it's fun, and your definition of fun changes as the years go on, I guess, as technology goes on. But very much the point, you want to baseline your models there. We had an interesting result technique there. By mistake once, you were working with meters, Newton millimeters, kilograms. I wanted to work with millimeters. So I didn't do my conversions correctly. So basically this flask had a density, something like a dark star. So it came down and hit the target and just spread like a cowpat all over the target. So, but the thing was, because it's an explicit solution, the time taken to run was very, very fast because the density was so high. And I thought, this is actually a good shakedown. Does the contact work? Yes, it cow splats against the target, so the contact works. So that became like one of my checks, to bang the density up to something crazy, check it out. So, these kind of techniques become kind of interesting, because I'm so fed up with something passing through something else, because again, the lack of graphical interface, you're relying on your data set up there. There was no visualization of the contact. So
So when did you start to use graphical user interfaces then? What kind of thing were you looking at there?
Well, the first one was, I mentioned that at Lloyd's Register, looking at the results.
Okay.
Graphical interfaces I was working at Hunting Engineering from about 81, 82 onwards. And I think that's where, again, using PAFEC, and then we transitioned into something else. I can't remember what it was now, but PAFEC had, they called everything dogs, pigs, rabbits, whatever, their sub modules. And one of them was an early graphics interface. So it wasn't interactive in the sense, oh, yes, it was. It was, I remember now, it was digitizing tablet. That was a huge breakthrough. So you still had the paper drawing, put this up, but you could take a Z plane and say, on this Z plane, you go pick, 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 pick. And on the Tektronix 4014 green screen, it's coming back to me now, you'd actually have that kind of paper doily of that Z plane. Then you move to the next Z plane. And so you're doing slices through like that. Then you say, okay, now comes the tricky bit. Now I've got to join this up in a 3D sense. And that was then handwork on the screen, picking that point and that point and that point. But all with mesh, no CAD. It's obviously direct meshing on the geometry bones coming from the for the paper drawing. So the digitizing tablet was a huge breakthrough, something that would take maybe a couple of weeks to put in complex weapon system. Now we can actually start to digitize it. Maybe only took 3 or 4 days instead of
I can remember the first time I ever saw a CAD system would have been in 1990. So I did an apprenticeship with British Aerospace very early on, pre-university, or leading into.
That was at Wharton, wasn't it? Or was it?
No, that was at well, it was called Chester, Broughton. I'm from North Wales, so it's where the Airbus wing facility is now.
Sure.
And they had a digitizing tablet, and it was called DOGS. I do remember that drawing office graphics system. Is that the same?
Yeah. So that would be part of the PAFEC.
Yeah,
thing,
okay.
probably. Yeah.
But I think that was definitely for CAD rather than for FEA.
Oh, okay. No, no,
Yeah,
you're right. I remember that now. Yeah, I can't remember who made that. Yeah.
yeah.
Yeah, that's interesting.
Scary thing, really scary. It might as well have
Yeah,
been the whole thing might as well have been in Japanese. I had no
yeah,
idea what was going on.
yeah.
But,
Well, the first CAD, automated CAD systems I remember it was CADS 4 and CV, computer vision, and they again at BA Stevenage, they were kind of competing. And the drawing office, the design office was really, they were still thinking consistent 2D views. So you'd have, your third angle projection. You're working with the three views simultaneously,
yeah.
building up this 3D model.
Okay.
But you never saw the well, you could see the 3D model, but the thinking was build up the elevation, the side view, and the plan view.
Yeah,
And the power was you could do this now. So projections, intersections, and so on became very slick instead of
yeah,
doing it, the manual way. So that
yeah,
was really the first approach to it. So it wasn't solid modeling. And I can remember CV and CADS 4X, something like that. They were coming along like that. And I actually went on a 3-week drawing office course to be able to drive one of those tools.
yeah,
But the trouble was, after a few years, we had the ability to describe geometry, but there was no way to link it to an FEA product. There was no way to link it
yeah,
forward.
yeah.
The one that really stood out was SDRC's Geomod, which was about the earliest solid modeler, Boolean operations, the idea of primitives, cutting, and so on. But it didn't go anywhere because it didn't talk to anything else. It didn't talk back to the CAD system. It didn't talk to FEA. So I remember I actually commissioned this, and we had licenses for a couple of years for this. But what we ended up doing, it was okay. It's no use for actually linking to CAD, linking to FEA, but it's very useful for packaging. So packaging all the systems inside a missile. And I remember there was a guy, a really nice guy. He was a young guy at that point. We said, okay, you're the packaging expert. And he had a great time fitting all of the components in together because there was no way of doing it up to that point. And then I remember CATIA coming through, and we had an early look at the CATIA product, and it suddenly thought, oh, wow, this makes sense. It's a solid geometry based approach. And really the essence of what we've got today.
Yeah,
This was
yeah,
before SolidWorks, before the others, and so CATIA really was a groundbreaking. And I remember 2 or 3 of us in the stress office saying, "This is exactly what we want," because now we're not thinking consistent 3D views. We're actually dealing with the guts of a solid geometry. It took a long time for that to get into the FEA world of saying,
yeah,
okay, I've got geometry, and the function of the geometry is to mesh. My end product is always going to be a mesh. I'm not,
yeah,
solvers, as we all know, can't understand what geometry means. We want mesh. To get that transition took, it wasn't, I think, until 2005, 2006, we started to get reliable, consistent meshing kind of coming through. So it was a very long transition period. I'd say from when you're talking about early 90s, no, really, mid 80s, later 80s, because the CV and CATIA first came through for me like 85, 86. So very long transition before we got something which could reliably give us geometry to mesh with.
Yeah, yeah. So did in terms of CATIA, I've often wondered this. Did CATIA or Dassault Systèmes, the developer of CATIA, did it come from Dassault Aviation? Was CATIA developed for their own aircraft programs?
Yes, it was.
And
Yeah.
was commercialized. Okay.
Yeah.
Yeah. And then became the CAD tool that's used throughout most, well, maybe not these days, but most of the aerospace industry, looking back a few years.
And what's interesting, there was there were a couple of trying to remember who it was now, because I wasn't, was paying some attention to the CAD side, but there was another product we had, which was it was either out of Grumman or I don't think it was Boeing, but there was somebody had a CAD system which was a similar kind of idea. It was coming from an aircraft company and then getting kind of commercialized.
Yeah.
And that kind of links back to what happened with that Wharton general displacement method. We had Ian Tague, Ian Kerr, pioneers, Phil Brightman. They put so much technology and knowledge into our system. But as I mentioned before, it suffered from the usual thing. We're an aircraft company producing aircraft. We're not a software company, and they're two very different things. So Dassault made that transition from a tool which is very good from within an aircraft company, as you're saying, within Dassault, to something which became a viable software product in its own right. And doing that transition, I think I've probably seen, 15, 20 products that I mentioned. All of the aircraft companies in the UK had their own. There was GASP, there was all sorts of strange names and so on, which were great tools, but they never made that transition to a production piece of software. On the FEA side, it was Nastran, who they commercialized it on behalf of NASA, really. So for a product to come from roots, which is good, it comes from a roots where the need is there, and it evolves from those roots, rather than somebody saying, let's write a spec for our clients who are sitting over here. And I think that's often the case, isn't it, with software these days? We think we know what those guys need. We're going to tell them what they need. We'll write the software, and then the end user picks it up and says, well, that's not what we want. So in some ways, it's it's very fruitful transition from in-house to something which is a commercial product. Very interesting history.
Yeah, absolutely. Yeah, it's fascinating. Like I say, Nastran is the obvious one from an FEA perspective, isn't it? But yeah, I knew a little bit about where CAE has come from. But these days, I mean, the big software vendors, whether they're CAD, CAE, whatever, they are standalone companies, aren't they? They may have elements which have roots in some industrial application, but how many? There aren't many software companies who also build aircraft.
No,
that's
right.
That's a big deal, isn't it? So when did 3D CAD, or the ability to take 3D CAD from or 3D data from a CAD environment into an FEA environment, when did that start to happen then, would you say?
Well, it started quite early on with flat file translations. Like IGES is perhaps the most earliest example. I think we were seeing IGES files come out, I want to say late 80s, early 90s. I haven't done any kind of background research. There's all a little bit
not at all.
But those, we had tremendous difficulty because it was trying to take this IGES flat file and turn that into geometry. It wasn't solid geometry, it was like wireframe geometry. The first then I mentioned Geomod, which was like a full start, and I was sad that SDRC didn't push that further. It didn't seem to be integrated within their suite, because they had ideas, or SuperTab. SuperTab was a superb preprocessor, but it was geometry less. And Geomod was the geometry, but they didn't fit together. And then the PDA came out with Patran, essentially. And Patran we had a look at again in the mid 80s, probably 86, 87. And that I liked because it had the geometry in it. You were actually building geometry from scratch, as it were. You're doing it in an interactive way with like a command line list initially. There's no 3D interface. Nevertheless, it was producing the geometry. And it started to be, you could do some meshing from it, but it still wasn't very slick. I think we dropped Patran in favor of SDRC for a couple of years because, again, the geometry was going nowhere. It was powerful within Patran, but it didn't talk to anything else. And then gradually that evolved into geometry, which could talk to other, directly to meshing and so on. And then the Patran product that came out evolved, has continued. I think it was 1990 when I remember they turned that into an interactive system, and it broke. So for about 2 years it was unusable, and then it got good again. So it's been a long, tortuous evolution to that. To say comfortably dealing with a solid body entity within CAD, exporting that out or directly meshing on that, probably not till 2005, 2006, something like that. So it was a very long gestation transition period that we saw there. And now, of course, it's completely, it's a solid geometry world.
Yeah, of course.
For most people. Although I had some clients 2 or 3 weeks ago saying no, they work from not 3D because it's all, I don't want to say exactly what it is, but it's all, let's say, space frames, grillages, things like that. More of a kind of like a civil engineering type of steelwork type structure. And it doesn't fit to be working with solid geometry. But I think probably, what would you say? Probably 90% of clients are working with solid geometry as the basis.
More so. You know, there were very few. I mean, I have been working with a company in the marine industry who have lofted 2D drawings of a ship structure that they'll build their surfaces from. You know, but the original design definition is in those 2D lofted drawings. You know, yeah. So, well, actually, one quick question I'd love to ask. Because I have a background with MSc myself, of course, you know, so I was involved with Patran support, you know, early 2000s, you know. Somebody once told me that Patran, the name Patran, came from patches for Nastran. Is that, do you know anything about where that name came from?
It was something translation. I don't think it was Nastran because Patran originally was a neutral product. It was positioned to actually handle anybody's, you know, and they had a whole bunch of, and they still have a whole bunch of translators going out to, you know, whatever you wanted to be working with. So that was the idea. And I think the strong link with Nastran only came when, you know, MSc acquired PDA in the mid 90s, something like that. So yeah, it was you had to define your geometry almost like you would define meshing. So it was, you know, you'd start with a patch, which was a 2D patch, and then you'd extrude that 2D patch into a 3D entity. And you're basically lofting and working in that way. So the end result would be a combined model which had been Boolean together. So it had similarities to a lot of the, I guess, the solid geometry we see today. I've forgotten the name of the engine behind it now, but it was rational B-spline, I think, basis, NURBS, all these kind of tools were being used. Again, this was like the mid-80s. I remember purchasing that for BA Systems or BA Stevenage in about 85, 86, something like that.
I mean, that must have been pretty radical at the time then.
It was, yeah.
Mm-hmm.
And you had a distinct process you had to go through, and then I can't remember. There was like a noodle rule, which people watching now will say, I know exactly what that means of my ilk, my age, and it was a process to develop this geometry. So it was, again, it was very good. But the trouble was, you know, you could build beautiful geometric models, but then could you mesh them? And that was one of the key things. And I think within that Patran environment, and I'm sure other tools were developing the same way, but I happen to know a little bit more about Patran. As a kind of it became like a universe on its own right. So the geometry and the meshing was you know, nice and kind of seamless, but then you couldn't talk to anything else. Now you want to bring in a CAD model into that environment, and now the fun starts again. It's an IGES import or whatever it would be. So this general purpose interchange of solid modeling is something that's really got slick, I think, only really over the last maybe 10 years or so.
Gotcha. Okay. So I've got a copy of your, well, a brief copy of your resume here. So you went from, well, just from your LinkedIn profile. So you then were working directly with MSc, supporting their software usage within industry then. Is that fair to say?
I at 95, I got a job of rebuilding the support and training group down in Frimley in Surrey in the UK. Because of the acquisition of PDA and various other things, they kind of had to almost start that again from scratch. So that was my job. I did that till 2000. Then I moved with MSc to the US in 2000. I've lived in ever since. So I moved to LA and did a similar kind of job within the organization out of Orange County, Costa Mesa,
Yeah.
kind of set up. Yeah.
Okay. So you must have seen, that was almost the golden years, wasn't it? I suppose of Patran usage. So you'd have seen lots of companies doing some pretty interesting things with Patran and Nastran back then.
Well, it's interesting. To me, Patran was always a tool. Any preprocessor is always it's a way of getting the solver to do what you want to do.
Yeah,
The
of course,
guts of it
yeah.
always is the solver. So I take your point, and there were certainly some fascinating developments and great developments. But for me, it was always, it's a means to an end. So there's lots of tools out there that I really admire, in the pre and post processing environment. But it's what does the solver do? How do we
Yeah, okay.
get the solver to do this?
Yeah.
So I think my perspective would have been more the Patran is unlocking more of the capabilities within Nastran is the way I'd kind of view it, and being able to interact with geometry is the way I'd kind of rephrase your question, if you like.
Yeah, no,
and then there's all sorts of interesting things kind of evolved and developed. Yeah.
That's how I see Apex.
Yeah.
Apex is unlocking Nastran,
Yeah.
in a way that people haven't been able to do previously, whether that's in terms of functionality or time and efficiency, training, people getting up to speed with it. That's how I see it's a tin opener for Nastran,
But I think Apex is interesting because I kind of see where your question's coming from now, because I think that is a stronger workflow. It's a very interesting workflow from, I've obviously explored Apex a little bit, but it's a fascinating workflow that's being developed there. That I would say, I think, I take back some of my words there. I think that maybe transcends the typical pre and post processor, because you're imparting that workflow onto the Nastran workflow, if you like. As we've kind of talked before, it's difficult because you want to unlock the power of the solver, but then as the solvers have got more sophisticated, the things we're doing now are more sophisticated. You need a workflow to wrap around that. And the trouble is, how do you define that workflow in a general sense? If you've got a client that you're aiming at, this is the product for that client, you can develop that workflow. But then you've got this client who's doing something very different. That client is doing something very different. So that's the challenge for software like a software environment like Apex, is to be able to be, this useful tool, as opposed to the old days of just the bare bones. I want to basically write out a Nastran deck.
So the workflow then was very, very much the same between lots of different companies. This is what people want to do. These are the steps you need, and there you go. Whereas now, like you say, every man is different. They all want different functionality, using maybe the same solver or not, but it's difficult to prescribe that workflow that works for everybody.
Because some are going to be big assemblies, where you're working now, and it's this interesting transition, I think, over the last 10 years. 10 years ago, maybe 15 years ago, it was more component based, because the CAD environment was, you've got a part, defining the part's good. Now the power of CAD is extended to now being able to deal with and handle assemblies. So as a consultant, you get an assembly now rather than a part. So again, for the preprocessor, it's like, how do we now work with assemblies? Like with bolts and rivets, I've got hundreds, if not thousands, of bolts and rivets in this assembly. So that was a really great question. How do I handle this on the preprocessing side to be able to build a model with all of those entities within it? Instead of back in the old days, well, we're going to ignore them, or we're going to put them in by hand and have very, very great simplification. So, and again, the sophistication of the analysis, this analysis chaining. I want to do, let's say, a preload. I want to do a thermal analysis, then I want to step into a nonlinear analysis, and then this chaining of analysis types, spawning different analysis has become very much more of a complex environment, and people expect to do complex nonlinear analysis out of the box using this
Yeah.
let's say this pre-solver and post environment. And if you said to a lot of people, perhaps these days, pre, post, and solvers, well, it's isn't it all analysis? So maybe these are old distinctions or old definitions we're using. So it's certainly becoming a much more complex world. And hats off to these the developers such as Hexagon, such as Siemens, such as all the other solution providers who actually to actually come up with a product which does all these things at minimum cost. And I probably raise a few eyebrows here, but the costs are down compared to the so-called glory days of the 70s or 80s, where people would charge what they like for software on those, because you're sitting on a 15 to $20 million mainframe to do this analysis. So I got to pay $500,000 for the software. Seems like a good fit. Now I've got a $600 laptop. I'm much more focused on the cost. So to in this day and age to come up with something which is good, credible, and progressing, best in class, I think it's quite a juggling act these days to get all those things together.
Okay, good. Well, that was a great background to part of your career. I mean, obviously you've been working in a consultancy capacity, and do lots of teaching with your work with NAFEMs as well. So I'm just going to ask a couple of the other questions I wanted to try and get through. This first one, which take it whichever way you want, really, but what do you think is perhaps some of the best use of simulation that you've seen? That can be workflow, process, software, whatever. But where have we seen the biggest advantages, or what are the best things that you've ever seen come from a simulation? I know that's a big question.
I think, it is a big question. I think being able to sharpen, if I think aerospace, for example, lots of fantastic aircraft were designed without simulation at all. We say that, but there's still people still doing, basically aerodynamics, performance, stability, structural configurations, and so on. It was all hand crafted work, so it's still it's obviously test linked in that. You could call it kind of simulation if you like, but our kind of meaning of simulation in the modern world, we then sharpened, enhanced, and focused those aircraft. So if I look back to the say the stress office at Wharton 50 years ago, I think it now means, in terms of performance of those aircraft, if we take like the Typhoon, I've never worked on Typhoon, but I've just admired it from a distance. This is the agile, combat aircraft, the European fighter aircraft. It's high alpha maneuvers, the huge aerodynamic loading coming on that, the configuration changes, the thermal performance, of the engine, the store carrying capability, all those kind of things, the optimization that's gone into that, the composite content where it's important and so on, all that can be achieved with tremendous amounts of simulation. And I think this is where simulation, a broader front, we're doing our bit with structural simulation in there as well, but I think the whole configuration simulation is really means that a system like that can evolve. And I'm seeing things such as Tempest, the UK thing for the future. Half of me thinks, why are they spending so much time with simulation across the board? They haven't actually cut any metal yet. But then the other half of me is saying, well, they don't want to cut any metal till they, it's perhaps the evolution of all that simulation. You're going to have a fantastic tool, an aircraft system, which is really taken us forward. Same, perhaps the automotive industry is another good example. There, for example, on the crash worthiness side, they're not doing physical crash testing until they really need to, and it's all. And I just working with a couple of clients on that field. If they do a crash test, a physical crash test, and the results are very different from their simulation, heads are going to roll. They expect to get it, very, very precise there. So that whole simulation underpinning that, meaning, in terms of vehicle safety, tremendous improvements in vehicle safety. And some companies such as Volvo, such as Mercedes-Benz, there's so much focus on safety there, and they can do that because of that, bringing together all those simulation techniques. So I think those are probably, and perhaps that automotive industry is a better example, because that's kind of helping mankind generally rather than combat aircraft. So I think that would be an example where we can do things, extraordinary things, not capable of being done. Say 20, 30, certainly 50 years ago.
I mean, that I do have another question here. How did aircraft fly before simulation, and how will contemporary tools enable them to fly more efficiently in the future? I mean, it's all part of the same response, isn't it? Okay. I mean, the key thing there for me is that the concept of using simulation just becomes so much more early on within the design cycle, to the point that it becomes a massive operation on its own before, like you say, anybody cuts any metal to need to do anything. I mean, that's a massive change, isn't it?
It is indeed.
In the 25 years I've been working with simulation, it was early on, it was very much a verification activity. Does this thing work? Now we've built it. Whereas that's flipped on its head completely, isn't it? Does this thing work in a simulation environment before we turn the light on in the factory? That's the thing, isn't it? Massive difference.
But there's a corollary to that, isn't there? And we've talked about that before. If you get to the stage where you assume that you can just press the button and simulation will derive your product for you, without that human interface, that engineering interface, that kind of background knowledge, I think we've seen this kind of evolution, and we want that evolution to keep going, but we don't want to revert back to, there's all these lovely science fiction stories about, cultures that are completely forgotten how the computers that control their lives, actually where they came from. And now they're totally dependent on this, these computers which were designed by long dead people and so on. It's an extrapolation, but I think it's a fun one. We've still got to have that engineering and common sense input to kind of baseline always what it is that we're kind of evolving into. And I think that sometimes people kind of forget that with the excitement of, and again, I think we've talked about this, new engineers coming in with the pressures coming from the vendors to say, this is easy, point and click, point and shoot, press button analysis and so on. That's like, whoa, okay. Maybe, but you still got to make sure that, that due diligence is followed, and this thing makes sense from a physical point of view. So it's always kind of going back to check the physics on that.
I mean, that the second part of the first question I asked, in terms of the most amazing things that you've seen, what would you say are the worst things you've seen, the biggest areas for pitfall, the biggest dangers that people can have with simulation? Do you think it's linked in with the sort of education, the background people have before they come in, or are there other things that could cause concern?
Sorry, I kind of strayed into the second question. I think at the end of the first one. That's the biggest pitfall. I've started to see. I've had to do cross-check analysis of various people's work where they've basically bought the tool, or got a license to the tool, and these days you can pay them weekly or monthly or even hourly. Said this is the tool for the job, and then come up with an analysis and predictions to qualifying the designs, and it's in the one case it was just complete nonsense. The physics were described wrongly, the background was all wrong. And then asking simple questions, it was clear that it was almost, here's the specification. It's like, this, they want to do a strength analysis, thermal analysis, a CFD analysis, couple these together. There's the product, there's the CAD definition. I've got this tool, so I just kind of feed it all in, and this is the answer coming out. And there was no verification of the answer. There was no validation of the answer, meaning, you know, compared to real world experience, whatever. And so even the most fundamental question about, well, why is that stress level there? You're saying that's the peak load or the peak stress through this time history. Why is it there? You know, what's the build up of the background? It's almost like cherry pick that answer out at that point. This is your answer, and then driving the design modifications from that answer. And that was really scary. I'd never seen such an abstraction of a job to that level, where then the point was downstream design implications. There it was kind of changes because the design was considered to be under strength, let's say. But then, you know, there's all that downstream work that follows from that. And it was like, okay, this is the trigger point for all this downstream work. Maybe millions of dollars of downstream work, but we're not paying attention to what triggered it. It's maybe a $5,000 contract to prove that point. Whereas, you know, it was all, I won't use the English phrase, but it was all the wrong way around. It needed a full justification, full qualification to say if we're going to act on this. And if it had been the other way around, if it had been a sign-off saying this is adequate, and then in fact it wasn't, then, you know, this is something that we would. Now this I think was a particularly egregious example, but it was just, you know, it was a bit of a wake-up call to me. This is about a year ago, and I thought, whoops, if this kind of thing is getting through, how can we, you know, overcome this? And I think it's the push to speed, efficiency. From the software vendor's point of view, they're trying to make sure, you know, it's pitched as being an easy tool to use. My analogy is always, well, here's the latest kind of like drill for drilling holes in something, whatever it might be. It's easy to use. It's kind of cool. It senses the speeds and everything else. You go and drill a hole in the wrong place, or, you know, drill through, you think it's gonna be a brick wall, and you hit steel, or the other way around. You know, you can mess up using that drill. So I think I have the same kind of feeling for a lot of the software tools now. They're very slick. They're easy to use. A lot easier to use. A lot friendlier, but you can still do damage in the wrong place if you misuse them.
Garbage in, garbage out, more quickly and more easily.
I'm all for, you know, efficiency and speed of tools and friendliness of tools, because I'm sure we both used software input, you know, for the FEA input, where the syntax is so horrendous and the data structures are so horrendous. You think, whoa, this is a nightmare. So now you have these easy, slick pre and post processors and working environment. But, you know, the tool is still the same tool at the end of the day. We've got to make sure, you know, we're not misusing it. So please, don't, anybody who's watching this, don't think I'm saying, let's go back to the mid 70s and late 70s, early 80s. They were horrendous for data preparation and so on. You guys today would just say, you know, I don't want to work in this field. We used to lose people from the stress office. We would try and get people to come into the analysis team. After one analysis, they'd run through. I'd say, "Do you want to ready to do the next one?" No. And they'd run off to do the, you know, the detail stressing job or whatever it was, because it's just such
they're done.
burden.
Okay. No, that's interesting. I mean, where do you see simulation developing then? Where are we going? You know, what people talk about AI and machine learning and blah blah blah. Are these just the latest trend that people are jumping onto, do you think? Or, you know, do you think there's big advances we're going to see in the short and medium term?
I think so. With the caveat we just talked about, that we're getting a tool which is getting better and more sophisticated and so on, but you still got to make sure that it's not being misused. I remember at Rolls-Royce, I talked about, you know, dropping flasks onto concrete, things like that. The number of oblique angles and the, you know, the fit and the type of target and so on is a huge variation. You can only afford to do a couple of tests. You can only afford to do, in those days, a few analyses. So I actually commissioned a neural network program to be written to actually take the reaction force history signature through time and say, these are test results from 3 or 4 tests. These are a whole bunch of analysis we think are reasonable. And then use that as a like a goodness fit to say, this doesn't make any sense. So the reaction time history coming from this, it's a similar kind of product, a similar kind of configuration, similar kind of drop height, similar kind of target, to suddenly get this wild spike coming in, it was like an indicator there's something wrong with the data, with the analysis.
Yeah.
So that's
Yeah.
one example, and I started to see that now. And that was neural network approach. That's what we called artificial intelligence back in the day there. That is very interesting to say, does this, and you're always interpolating. So this is the range of data we've got. Does it fit within this? Extrapolating is very, very, very dangerous because it's a wild world you haven't investigated. The other thing is that, like a rules-based. So trying to think, setting up nonlinear contact can be a nightmare because there's so many different drivers. So the software companies now have these kind of overlay buttons to say this type of contact or that type of contact, but like broadly, like, is it mildly nonlinear, is it aggressively nonlinear, and so on. They try and pull together the settings, and there might be sort of 10, 15 settings to say that matches that profile. So rule-based approach would say we've trained and we've looked to say this is now the way to go to the best fit for these settings. So I think that's where AI could be really, really useful, where you're learning from a whole field of different results to say this is, instead of having like a fixed pattern of settings, you can start to adapt these settings. Or like with time step adapting, instead of crude primitive ideas we have at the moment, more kind of learning from overall industry experiences. Or you're a company, get a summer intern, get them to run thousands of jobs, and then you've got your learning data to use from there. So I think there's all sorts of things where you can actually start to guide the processing through. The simplest thing is like, for example, in dynamic analysis, when the Lanchos first came out, you had to have all sorts of I call them presets, if you like. So is it solid elements? Is it this, that, and the other? How much memory? Excuse me. How much memory have you got, and so on? Now the solvers are intelligent enough to actually go and look in the system, so you don't have to ask the user to type in what they're doing. So they go and search in the system. So that's just the start of things I think can be done to actually get a better decision making, like machine decision making, based on a kind of rules-based network approach, neural network kind of approach, training things, and so on. And I think that there's a lot of scope in there, because otherwise, is it black or is it white? Well, we don't know. So why not have shades of gray, which can actually get more subtlety in there? So I think there's all sorts of interesting developments which will come through. And as I kind of teach, it's quite funny. I was teaching a nonlinear class the other day, and I suddenly thought this would be a great place for AI, where it's difficult to actually to bring a binary answer to that, like a series of switches or a choice of what we're going to be doing. Maybe we can gradually learn, what that could be. For example, like a stress concentration. If it's a particular profile, knowing the geometry, knowing the stress gradients we've got in there, stress field, knowing the type of elements, there's no reason why somebody couldn't, couldn't figure out, again, interpolating from existing known data, what that stress concentration should be there with, say, a coarse mesh. Things like that could come through. Now, there's a lot of, we can make sure we got that right, but I think the principle is there.
Yeah, there's tons of scope, isn't there? I mean, just you mentioned the example. I think you said the $5,000 check to make sure that the downstream work. Things like that. Wrapping some kind of intelligent framework around something, whether it's the engineers themselves or whether it's from a third party where that knowledge has been gleaned or developed. That's definitely something.
I mean, that would be a specific example. Here's the results of that analysis, and it's basically a convective heat transfer coefficient was implied. This much heat is being dumped from the system. Well, my question was, what is the effective convective heat transfer at that point? How does it relate to normal hand calculations? And there was no possible way of getting back to that. You're like a data probe saying, okay, you assess that and tell me what the equivalent one-dimensional convective heat transfer coefficient would be from that point. Is it within sensible bounds? Maybe therefore checking the whole of that surface field to say, convective heat transfer coefficient implied is within sensible bounds, things like that. Great tool. Yeah.
Yeah.
Hey, we've just
No,
invented something there, Steph. We need to patent that now.
Well, like you say, in terms of the way technology is developing, it's difficult to keep abreast of everything that's going on, isn't it? It really is. I mean, you mentioned before we started the call that you'd looked at a number of different pre and post processes, and just that task in itself takes a significant amount of time just to understand what they do and how they how one
to
can
get the best out of them.
Exactly. So it's difficult to keep abreast of all this technology, isn't it? So
well, I would say I can keep one pre and post in my brain at a time, and as I typically work with maybe 2 or 3, I've got to kind of put that one aside for a few months and then forget. As I get older, forget the implications of that. Then major on this one, get really slick and efficient on this one, and then a different project, now I've got to turn to this one. So it is a challenge, and but I must say the learning curves are getting better. The learning curves used to be a total nightmare, particularly when it was like text input and so on.
Question that sprung to mind, and probably we're coming to a close now with what we're talking about, but given all the stuff that you've seen and the experience you've built up over the years and different tool sets, methods, computing capabilities, all this different kind of stuff, what would be some sort of simple advice that you would give to a young graduate, maybe not graduate engineer, coming into a design development environment that might want to look at simulation? What sort of things do you think people should be focusing on these days? I've put you right on the spot there, haven't I?
Yeah,
that wasn't even on the list of questions we
you gave me a quick 2-minute preview on. I think keeping in touch with the product is absolutely essential, and keeping in touch with the physics implied with that product. What is this component, this vehicle, whatever it is, what is it supposed to do? What environment does it operate within? And then as we start to do our simulation, what is it we're actually trying to demonstrate? What is it we're trying to kind of prove? And can we break that down into simple kind of baby steps to start with? And then is the simulation in step with this? And I think the fundamental piece of advice is that every simulation is guilty until proved innocent. That's kind of a saying I've had for many, many years. I don't trust anything coming out of this analysis until I can get that kind of warm and fuzzy feeling about it. Now, that might be a very simple kind of sanity check, like I was talking about with the convective heat transfer. It's a plausible range of a very complex analysis, or the frequencies involved seem to be feasible, or the stress level seems to make sense. So it's always being somewhat cynical about the results that come out, and not believing what we see until we get that confidence. And it goes in this way: you build up your own confidence level in that result, and then you can start to pass that on to other people. You can start, the checker, the reviewer, your lead engineer. You can start to build that up. And I think the other thing is, keep it simple. If it seems like a daunting analysis, then break it down into maybe simpler substeps. For example, you might be doing a complex dynamic impact analysis. Well, maybe it's useful to run a static simulation of just that thing under an inertia load, just resting against the body. So it's just a static analysis to make sure the load paths are working, the contacts working. Get some, you're getting into the structure, getting into the components, you're seeing what comes out. Maybe that an early analysis is not very relevant or valid to what you're going to be doing next, but you're beginning to kind of sort of shake the shake this thing apart. You're beginning to kind of get into it a little bit, rather than saying the task is to do a transient nonlinear analysis with nonlinear buckling, contact. There's some thermal implications. And I want an acoustic signature coming out from the bang, and all that. Don't jump into that. Break it down into steps. And check the physics at every stage that goes through.
That's something I've often thought, is that there's almost like a sexiness to going full bore for this really
Yes.
complex analysis.
Yeah.
You know, people
Yeah.
think, you know, if you know, you've done a linear analysis, that's not good enough. It needs to
Oh,
have,
it's boring.
or
Yeah.
yeah. You know, and I think, you know, to something, well, not that long ago, you know, when we're developing some wing structure for a commercial aircraft development program, and you know, people were saying, linear, why, you know, blah blah blah, how can you do this with linear? And I'm like, well, because we've got 30,000 load cases just to start off with, you know.
Yes.
We need to design this thing
Yes.
to work. We can look
Yeah.
at the, you know, the complexity of whatever analysis we want to look at if needs be, you know, if a problem arises, but we want to design the thing to work in a simple way, so we don't need to rely on these really complex, you know, solution sequences to get us to a final design. You know, I think there is a danger of people getting sucked into the complexity too early with these things. You know, like, keep it simple. You know,
Yeah. Yeah.
that's something.
Well, I must admit, you know, having said all this myself, I get, you know, a consulting project comes through and you've got the CAD model, and it's almost never. I've got to remember to sit down on my hands and just look at the geometry and assess the geometry, read the specs, see what the component, what it's trying to do, what the job of that component is, what the operating environment is, and not go mesh, because it's almost an overpowering temptation to say, I want to see a mesh on this thing. Will it mesh okay? You know, and so you think, I got to stop, because that can be 2 or 3 days, you know, and you're just focusing on the meshing. You haven't even sat back and thought, what's the objective of the analysis? What are we trying to do here? Can, you know, all these, you know, good things we talk about. So yes, indeed, it's like, wow, it sounds like a really exciting analysis. I want to see animations and nonlinear behavior and all this kind of thing going on. And it's like, yeah, and your client is also now indoctrinated in the, you know, seeing all these fancy animations and this result and that result. They're expecting to see magic before their very eyes. And maybe your lead engineer is expecting, well, where's the, you know, where's the stuff coming out? Do I have a time for a quick 2-minute story?
No, that's fine. Yeah, you go for it.
Yeah. Okay. Many years ago, again with Rolls-Royce and Associates, we were doing early impact analysis on these flasks and so on, and nobody had really seen animation, so we were actually having to get we're getting animations on the screen, had to have a video camera. In fact, I think it was either video or later film camera, which had to be strobe synced to the refresh rate on the screen. So you set up this big complicated camera to be able to get the animations off the screen. There's no other way of doing this. This is like 91, something like that. Somebody's going to say, well, we could do that, but we didn't, at Rolls-Royce didn't have that facility. So we kind of got the final animations prepared. So probably a week of preparing this. I had to go down to the Admiralty to present our overall safety case. I won't go into specifically what that was about, but it was like a long day. Basically very senior Navy types who were sitting around. Most of them, you know, I think the idea is if you become a captain in the Navy or an admiral in the Navy, you've got so much background, common sense and sense of what makes sense, you know, that you don't have to be an expert. They have the engineering experts, but then also these, you know, just people with tremendous amounts of real world common sense. And I can remember we went through our justification about why we thought this was safe and the tests we're going to do and so on, you know, to dare to put this equipment in their submarines. And we came to do this animation. I showed the animation, and I remember it came down. It was spectacular because it was an explicit analysis, so things broke off, bits, you know, bounced around and all this. And I remember this admiral saying, my goodness me, that's so accurate. That really makes sense. Look at that fragment bouncing off there. That looks so realistic. And I remember thinking, it's completely arbitrary, you know, the way that the elements split. We got an energy criteria, which I kind of half invented and kind of dreamed up to say, this is, I think, what's going to happen. You know, the overall reaction forces and the overall energy transfer was right. But that particular fragment coming off was just, I could say it's a fragment of the machine's imagination, you know, but he was sold on that. As soon as he saw that bit come spinning off and so on, I thought, he was on side from then on, you know, like a jury. that jurors on our side, you know. I just thought this, yeah, I'm pleased, but on the other hand, you know, it's like, whoa, you know. So that's the danger when you get these, you know, we're talking about, you know, the elaborate analysis that looks so good, you know. Now we got streamlines flowing through the CFD, we got, you know, heat transfer going on and so on. It's beautiful, but is it just a giant Disney CGI?
Yeah.
Or Hollywood CGI?
Yeah. Fascinating, Tony. Well, I enjoyed that. That was a good conversation. Yeah.
Yeah, we're gonna have to do a follow up at some point. Yeah,
We will. There's a. Well,
I'm sure if you prod me, there's. Did we get all the way through the questions, or no?
We got ballpark through most of them. You know, so thank you. Really enjoyed that. That was great.
It's been a pleasure. It's always fun talking to you, Steph. There's it's good fun. So yeah, it's a great industry to be in. So yeah, thanks again. Thanks for the opportunity.